We are diving into a really interesting NVIDIA paper today. It's called TiDAR, Think in Diffusion, Talk in Autoregression. And it tackles, one of the biggest trade-offs in LLM decoding right now, speed versus quality.
Exactly. Everyone wants lightning-fast responses, but nobody wants the model to start talking nonsense. That's the core dilemma.
So the big claim here is that LiDAR, this new hybrid architecture, finally cracks that problem. We're talking a speed up of up to, almost 6x?
5.91x faster throughput compared to its autoregressive counterparts like the Quinn models, which is just massive. And they're saying it does this while maintaining quality.
And the mechanism is just fascinating. It does two things at once in a single forward pass. It thinks in parallel using diffusion to draft a bunch of tokens.
And then it talks by using autoregression to instantly check them. It's all happening simultaneously.
Which, for anyone working on model deployment, is a huge deal. They're talking about using free GPU compute density, and critically, it supports exact key value caching.
That KV cache point is a game changer. It's been a real sticking point for most diffusion models.
Okay, let's unpack this a bit. We all know why standard autoregressive models, AR models, are slow, especially for real-time stuff.
Right, it's the memory bottleneck. You're constantly loading these huge weights and the KV cache over and over again for every single token.
The I/O latency just kills you.
It absolutely dwarfs the actual compute time. And because you're only generating one token at a time, your super powerful GPU is basically just sitting there waiting, especially with a small batch size, like in a chatbot.
Batch size 1, the classic scenario.
Yeah, the hardware is mostly idle. It's incredibly inefficient.
So that's where diffusion language models, or DLMs, came in. The promise was always this parallel decoding.
Exactly. The idea is, look, if we can generate, say, Dasha tokens all at once, they can all share the same weights and KV cache you just loaded.
And this gets to their concept of free token slots.
It does. If you look at GPU latency, it stays pretty flat for one forward pass up until you hit a certain number of tokens. It's like a bus ride. The cost is basically fixed once the bus is moving.
So you might as well fill the empty seats.
You might as well fill those empty seats, those free compute slots, with potential tokens. It costs you almost nothing in extra wall clock time.
But, and this is a big but, historically that parallelism has meant a huge drop in quality.
A massive drop. Because when you sample BOC tokens in parallel, you're using this marginal distribution, which the paper calls PDIF. It's a parallel guess.
And that guess assumes all the tokens you're generating are independent of each other within that step.
Right. And language doesn't work that way. It's like trying to write a whole sentence at once without knowing what the first word is going to be. AR models use a sequential distribution, PAR, where every new token depends on all the confirmed ones before it. It's just a more natural fit for language.
So LiDAR's mission was to get the speed of that parallel PDIF guess, but with the quality guarantee of the sequential PAR verification.
And they do it in that single forward pass. It's really clever. The model partitions its input into 3 sections.
Okay, what are they?
You have the prefix, which is the confirmed history. Then you have the tokens that were proposed in the last step. And finally, you have tokens being pre-drafted for the next step.
So how does the talk and think actually happen at the same time within that structure?
Okay, so the talking part is what ensures quality. It looks at the tokens drafted in the last step and uses autoregressive rejection sampling to check them one by one.
Guided by that PAR, that quality distribution.
Exactly. It's verifying which of those drafts actually make sense in the sequence. But while it's doing that sequential check...
The thinking part is already drafting the next batch of possibilities.
Precisely. It's using that parallel PDIF approach to pre-draft proposals for the next step, conditioned on all the possible outcomes of the current verification. It's happening at the same time, using up all those free token slots.
And the secret sauce to making this all work is the attention mask.
It's this special structured hybrid mask. Part of it is causal for the AR verification, and part of it is bidirectional for the diffusion drafting. It lets the model compute both sets of logits in one go.
A huge efficiency win.
It's massive. And it makes training way simpler. You can compute both the AR loss and the diffusion loss from the same data sample.
They also made this interesting choice during training to just set all the diffusion tokens to mask tokens. Why do that?
It sounds a bit extreme, but it provides a much denser and more consistent training signal for the diffusion part. It stabilizes the whole process, and importantly, it reduces the difference between how the model trains and how it actually runs during inference.
Which promotes that super efficient one-step drafting.
Exactly. It makes the whole system more robust.
Now, anyone who follows this space will immediately think of speculative decoding. methods like EGLE or the MTP in DeepSeek. How is LiDAR fundamentally different?
That's the right question to ask. There are a few key advantages. First, LiDAR is a single model.
So no separate, smaller draft model.
Right. The drafter is the base model, so it has high capacity. You don't have a weak drafter creating a bottleneck. Second, the drafting itself is fully parallel.
Unlike the MTP methods, which are still kind of sequential in how they generate their drafts.
Exactly. LiDAR's diffusion approach uses the full compute power across all those masked tokens at once.
And the third point is the single forward pass.
That's the big one. Speculative decoding is usually step 1, draft, then step 2. Verify. It's sequential. LiDAR merges them. It's verifying the last step while it's graphing the next one. No overhead.
I do have to bring up a limitation they mentioned, though. This approach of appending mask tokens means you're effectively doubling the sequence length. Doesn't that hurt, especially for long context?
That's a great point, and yes, it's the main trade-off they acknowledge. For shorter sequences, like in a chat app, the massive latency benefit completely outweighs the memory cost, especially since you're using otherwise free compute.
But for, say, 128K context window.
For that, yeah, it's a current limitation. They specifically say that extending this to long context sufficiently is future work. But this is where the next point becomes so important.
The KV caching.
The KV caching. Traditional DLMs like Dream really struggle here because of their bidirectional attention. You can't just save the history cleanly.
And LiDAR solves this how?
Because the talking part is pure autoregressive, it can handle the KV cache exactly like a standard AR model. It saves the cache for the verified tokens and only throws it away if a token gets rejected. It's incredibly memory efficient for deployment.
Let's get back to the hard numbers on speed. You said almost 6x. How many tokens is it actually getting per forward pass?
The raw numbers are really impressive. The 1.5 billion parameter LiDAR gets about 7.5 tokens per model forward pass, or NFE.
And the 8B model?
That one hits 8.25 tokens per NFE. And again, this is with almost no hit to quality compared to the base Quinn models.
And that high acceptance rate is what turns into that 5.91x wall clock speedup.
It's a combination of a high raw acceptance rate and, this is key, a much better conversion rate from accepted tokens to tokens per second. That's the direct result of doing the drafting and sampling at the same time.
This also fixes a huge headache for benchmarking diffusion models, right?
Oh, absolutely. Calculating likelihood for metrics like MMLU is a nightmare for most DLMs. You have to do all this inefficient sampling. But because LiDAR has that AR verification mode,
it can just calculate the likelihood directly.
Just like a normal AR model, which proves its quality isn't just smoke and mirrors, it's genuinely competitive.
Okay, what about the Pareto frontier analysis, where they plot quality versus efficiency?
It just confirms the story. LiDAR sits on the best curve compared to block diffusion and standard AR. It shows that amazing balance, getting close to the quality of a fine-tuned AR model, but spitting out 7 times more tokens per step.
They also did an interesting ablation study, fiddling with how much the model trusts the AR logits versus the diffusion ones during verification. What did that show?
What's really fascinating there is how stable it is.
Yeah.
It almost didn't matter. Whether you leaned heavily on the AR logits or mixed them, the quality and speedup stayed roughly the same.
So what does that mean?
It means the quality guarantee doesn't just come from having some AR knowledge in the draft. The real hero is the autoregressive rejection sampling process itself. That talking phase is an incredibly powerful and robust quality filter.
And just to close the loop on the full masking strategy from earlier, that was really about making sure the training process matched the inference process to squeeze out every bit of efficiency.
Exactly. A more consistent training signal gives you better performance, especially on tricky things like code generation.
So to be transparent, we should just quickly reiterate the other limitations they noted.
Right. The focus was very much on batch size 1.
Latency critical.
Latency critical. And they also noted that these amazing results are just with native PyTorch. With custom kernels, you could probably push the speed up even further.
So the big takeaway here is that LiDAR seems to have successfully married the speed of diffusion with the quality of autoregression. And for engineers, it solves some really painful deployment problems like that exact KV cache support.
It really does.
Yeah.
Which leads to, I think, a pretty provocative question. If you can now get high-speed parallel drafting and gold standard sequential verification all in one forward pass, really leveraging the hardware we already have, what's the future role for a purely sequential AR model in deployment? It really feels like, to be competitive, future high-performance models will have to be capable of this kind of dual-mode thinking and talking.